And I'm now going to introduce our first speaker, which is Alicia Cortes. And she presented yesterday in our monitoring program, which is part of UC Davis, the UC Davis PERC team. And they've been doing research out here in Philip for the past 5 years. And she's going to actually have 2 talks in the session. So one is providing an overview of some of the water quality monitoring predictive tools. And then she'll end the session talking about one of the aquifer restoration projects that is funded and being planned and going forward in the lake. So we're really excited, and let's welcome Alicia. Thank you.
Thank you very much, Angela. How is the sound? Can you look here to you? Oh, very well. Thank you. All right. So I think at this point, I'm gonna make a great introduction. My name is Alicia Cortes. I'm a senior scientist at UC Davis with Tahoe Environmental Research Center. And yes, as she mentioned yesterday, I talk a lot about measurements in the lake, in situ measurements. And today I'm going to talk about the exciting and novel component of this project, which is the development of predictive tools, the ones which can help us to understand how the remediation strategies that we are planning to implement in the lake will actually work and help with all the challenges that clearly is having, or at least help some of those, right? So with that, I would like to, here we go, to the next. Here, it says frozen. I'm gonna work. Yeah, no worries. You only need to come here just to have it. All right. So for those who attended yesterday to the presentation, this diagram is going to be very familiar. But just for the new people in the room, I wanted to remember and remind you of what the watershed and lake remediation project that UC Davis in collaboration with USGS have been doing within the past 5 years. And essentially, our program had 3 main components. So the first one was essentially continuous in-lake measurements in the system in Clear Lake, which is what we call lake monitoring. So I talked about yesterday, and I'm not going to repeat that, but essentially these continuous measurements in the lake have been essential to build these predictive tools, these black boxes for some of you, right, that essentially help us to understand the future. And those are, that component is what we call lake modeling. And this lake model has been, and is going to be continued to be improved by USGS inputs. Yesterday we talked about them, so I'm going to skip that part. But essentially, what I would like to highlight is that these predictions are ultimately going to help us to understand how restoration strategies in the lake are going to work in the future, also inform lake management, and help us to understand how climate change is going to affect our lake. So this is essentially the workflow of our project. And I would like to say that for this talk, I'm going to focus mostly on the 2 last topics that you can see here. So first of all, this has been repeated already several times through the whole symposium, but I would like to just hammer home and say that models are essentially simplifications of real systems. So we are trying to create a conceptual idea of how our system works, and then try to use it to reproduce the complexity of our system. And we can use many kind of models. And essentially here in this diagram, I'm showing you the kind of model that I have used to reproduce how the water moves in Clear Lake. So we call these kind of models hydrodynamic lake models. And essentially what we do is simulate, which is essentially reproduce how the currents in the lake and how the temperature is changing. Essentially, we are just trying to understand how the physical drivers are changing over time. And for that, we are parameterizing and reproducing processes such as the one that you can see here in this diagram, which are essentially the creeks that we just here in the previous session, how they enter and how they impact the lake. We also try to reduce the gradients in temperature in the water column, which we yesterday described as stratification. and also other processes such as mixing or exchange between the basins or simply heat exchange between the water and the atmosphere. So this is one of the models that we have developed. And just for fun, I would like to show you an experiment of what this hydrodynamic model could do in Clear Lake. And the video that I'm going to play right now is essentially showing you the shape of Clear Lake, as we all recognize. And imagine that we are going to add to the upper 3 particles, just in the middle, of the big hole. And we would like to know where those 3 particles in the lake are going to go. So we could use this model to actually track the path of these particles. And just for this video, I have tracked each particle with a different color, so you can see where they go. And as you see them moving, you can imagine that these particles can be anything, right? They can be mercury. We talked about mercury a lot yesterday. They can be gas. They could be any sediment particle that is moving around from creeks. So essentially, as the video progresses, those particles may end up, as you can see, in essentially completely different places, right? So this is essentially a way of highlighting that clearly is a complex system. The currents are really unique. And whenever we are trying to test any restoration strategy in the lake, we have to be aware that each year, each season, each week can be very different. So we need to use these kind of tools to really understand how our strategies are going to work in the lake. So I get this question a lot, by the way. Everyone is asking, Alicia, do you trust your model, right? And here is my answer. Yes, I do. Because I use on-the-ground measurements to ground truth my model, right? So here in these figures, I'm trying to provide a brief overview of how I've been proving that my hydrodynamic model is robust. And here in these figures, they are very colorful and a little bit confusing, but essentially what they are showing is time on the x-axis, the y-axis is showing you depth, and the colors are representing velocities. On the top, you can see model values, and in the middle, you see observe. So essentially, as you compare those plots, you can see that essentially the trends are very similar. And just as a confirmation of this, at the bottom, you can see time on the x-axis, bottom velocity on the y-axis, and I'm comparing model values in red with observed values in black. So essentially, you can see a good correlation of the currents that are happening clearly. So check, I'm happy with my currents. And on the other side, here on the right, you can see the same exercise, but for lake temperature, right? So on the top, model values, on the bottom, observed values over the course of 3 years, very similar trends. And essentially, I can tell you that we have run all our statistical values, and we have obtained values which are ranking the validation of our model as very good. So we are very happy with those results. But we don't only care about currents in Clear Lake, right? So something that we have learned through the whole 2 days is that water quality is also one of our main concerns. So another model that we have coupled to this hydrodynamic model is what we call a water quality lake model, which essentially is able to reproduce how algae is changing in Clear Lake. And for that, instead of temperature and currents, we are modeling and simulating nutrients, dissolved oxygen, bio, and also algae. And essentially, how is that? Let's click the button. So essentially, what we are doing is modeling and reproducing different kind of pools. And essentially here, this is a very simplified version of all the processes that we are parameterizing in this model. But we essentially have a pool for particulate organic matter that is connected to the dissolved organic component, then that's linked to the dissolving organic nutrients, and ultimately, they're going to be the food for the algae. And in general, dissolved oxygen is going to be also playing a very important role in this cycle. So this is the water quality model that we have implemented. And the same as for the water currents and the temperature, we have done the ground truthing of our model, right? So similar exercise, but in this case, instead of a very long time series, I'm comparing profiles, essentially because when we go to the field, we just grab water samples, and it's easier to compare pairs of measurements that we have in the water. And here what you can see on the left side is profiles, as I mentioned, of different variables in the x-axis as a function of height about the bottom, of temperature, dissolved oxygen, concentration of phytoplankton, and SRP, which is soluble reactive phosphorus. So it's essentially the dissolving organic phosphorus, the food for the algae. And the two lines that you can see are measure values in blue and the model values in red. So here, as you can see, again, we found a similar good correlation. And in this case, the statistical values that we run are ranking the comparison as good. So as we all know, biology and biogeochemistry is way more complex than physics. So it's totally normal that we are not getting the very good, but still we are very comfortable with the kind of trends that we are seeing. And just as an exercise and also additional information, I would like to explain you what you see on the right, which are essentially model values of different properties. And here what I'm showing is time on the x-axis, a depth on the y-axis, and the colors in all these plots are showing you different properties. And again, these are model values during one of the summers that we have been testing with our model. And essentially, I would like just to highlight a few things because essentially it's a summary of what we were all discussing yesterday during the half session. On the top panel, you see temperature, and you essentially see how the temperature gradient is evolving over time. So we are developing a stratification. Then in the middle panel, you can see how the oxygen is changing with temperature. So as we develop two layers of temperature, we are developing the hypoxic conditions at the bottom, essentially the low oxygen at the bottom, because there is no exchange with the surface. And as the DO is reduced, you can see that the SRP, the dissolving organic phosphorus, is starting to be released from the sediments. So again, this concept of internal looping, just for those who were in the room yesterday, is really coupled with oxygen. And ultimately, when the phosphorus is increasing and the temperatures are getting warm, is when the phytoplankton is increasing, which is essentially confirming that that ratio between nitrogen and phosphorus that we were talking the other day is essentially going down. And the phytoplankton is really hot and is growing faster. So essentially our model captured all our conversation from yesterday, which is a really good achievement. So yeah, I guess that's so far. I would like to switch gears and come back to my diagram, in which I essentially said that for this talk, we have developed a lake model. And hopefully so far I convinced you that we're very happy with the model that we built. And we trust it, which is probably equally important. But now we are ready to test restoration strategies to mitigate harmful algorithms in Clear Lake. And that's what I'm going to try to do for the rest of the talk very quickly. And here I have a list of the restoration strategies that to mitigate harms that different people have suggested to the DRC to obtain funding. So here you can read that some groups have suggested sediment capping, algae and nutrient harvesting, ultrasonic algae control, and hyperkinetic oxygenation. I will skip the last one for this talk because there will be another talk right at the end of the day. So if you can stick around and be with me by the end, I will tell you everything about it. So that's the remediation strategy that UCDAV has proposed. But for the other three, what I'm going to show is just only preliminary results. So I want to highlight that because in the results that I'm showing today, I'm making assumptions. And I have started conversation with some of the proposal components. Thank you, Dave, for answering my initial questions. And I'm so looking forward to keep the conversation open with other people to essentially refine those results and make sure that we continue the conversations to make sure that we reproduce the scenarios that we need. So jumping in, the first one that I listed, sediment tapping. I'm going to follow the structure that you see right in front of you for all of them. I'm going to give a brief definition, what the proposal proponents have recommended so far, which is essentially the pilot project, and then the model assumptions, right? So the things that I have assumed that require more conversations. So for sediment tapping, it's a technology that consists in the addition of phosphorus blocking and enhanced clay at the surface of the lake. And this material is expected to sink down in the lake and cover the sediments with the final goal of preventing internal loading, this concept that I was mentioning before. So the pilot project that the proposal proponents have suggested is to cover around a surface area of around 70% of the lake. And the model assumptions that I have made for this project is the density and the diameter of the clay, the particles that we are supposed to be adding to the surface. So here you have the values. We assume 50 micrometers and 1200 kilograms per cubic meter. And for the results, I would like to mainly focus on the processes that we found in our simulations that we believe that are compromising the efficacy of the technology. So essentially here in these diagrams, we also were around doing the mercury talk that Sergio Guardiola presented yesterday. These figures will be familiar, but essentially I'm going to steal a little bit of the work that Sergio presented yesterday to describe the things that may be compromising the efficacy of this technology. So the first thing is the fact that the clay that we are adding on the surface, because of the nature of clear lake, may be dispersed and not really settling down. And for that, I would like to just describe you here these cross sections that we had in an hypothetical case in which, for example, we have a layer of clay that you can see here represented by this very light blue. And you can see here in the cross section at the top. So if we add that at that specific location, and we let the currents move around for around 24 hours, what we see is that the material didn't really settle down. It started moving around, and it didn't really create the layer that we really need to prevent internal loading. So we think that dispersion and settling in clear lake are going to be really challenging for this kind of technology, and we just only want the group to be aware of that. And the other process that we found challenging is the resuspension. So it's essentially the counterpart of the other one. So in this one, if we add a layer of sediment to the bottom of the lake with the light blue, what we see after 24 hours, because of the natural currents in the lake, is that the currents are picking up that material. And the whole thing is full of clay, but is not really settled at the bottom. So here in the center, you can see my conclusions from this simulation runs, preliminary results again, that are the process is compromising the efficacy of the technology, which is that essentially because of dispersion, we are going to have less product reaching the target area. And also because of the resuspension, maybe a third of the project will be resuspended by the currents, and we are not going to get the shield of the sediments that we will need. So moving on into algae and nutrient harvesting, again, similar pattern. The technology is planned to be doing the removal of the algal biomass nutrients, both nitrogen and phosphorus and cyanotoxins from the lake between an inflow, that is essentially the water from clear lake, and then an outflow of water, that is essentially returning clean and oxygenated water. So the pilot project that is being recommended to the DRC is planning to test and to clean an area of around 0.1% of the total surface of the lake, so around 50 acres. It's going to be also close to Redwood Park, so it's an impacted area. So that's the target area of the lake. And they are recommended to use 1 million gallon per day harvester, which is essentially going to be running for around 3 weeks in the middle of the summer. And for this, for the simulations of this technology, what I've been assuming is that the intake of water that is going to be taking water from here is going to be essentially at the top of the lake only, pouring roughly 2 meters, so essentially the surface of the lake. And I have assumed 100% efficacy of the technology. So essentially, all the water gets clean, and everything is going to be running just from the surface. And here in this plot, I'm trying to represent a very simplified version of these preliminary results, in which you can see 3 different variables plotted over time in the x-axis, and in the y-axis you see the dissolved oxygen, SRP, the soluble reactive phosphorus, which is the same as orthophosphorus, and at the bottom you see concentration of phytoplankton. So the different wiggly lines that you can see are representing different scenarios. So the blue is essentially assuming no flow is changing between the lake and the harvester, so that would be our control case. Then we have the black, which is assuming the flow from one harvester, and then the red, which is assuming 10 times more the flow one harvester, right? So the preliminary results that I get, and I would like to say that these values are average in depth and across the 50 acres of the treated area. So essentially, it's trying to see how effective is the technology across the area that the proposal is suggesting. What I see is that essentially one harvester is making minimal changes, but then we can see the reduction in nutrients of around 50%. So essentially, we are just maintaining our baseline, and we are not seeing the internal loading that it would happen that summer. And the other benefit would be that the algae would decrease by 10%. So this would be the benefits of having that flow pumping and exchanging water with this technology. And finally, I would like to describe very briefly the conclusions from testing of the ultrasonic algae control. And just very briefly, and I'm sure that at some point they will give another talk to the group with more details. The technology is focused on using ultrasonic waves to control, to essentially apply pressure on the algae cells. So ultimately what they are trying is to kill the growth, right? So they are preventing the algae to evolve. So for my model, what I'm just saying is that the growth of the algae would be zero. The pilot project that they have recommended will cover also 0.1% of the lake. So again, they are trying to treat 50 acres of the surface of Clear Lake. And for the model development, the assumptions that I've made is that the layer that they are treating actually expands the average depth of the lake in the area where they are going to be working. So that would be roughly like 5 meters. But again, this is something to confirm once that they provide more input. And here in this diagram, I'm showing some results of what I see that the model is producing, very similar to what I showed before. So time on the x-axis, different variables in the y-axis, the different wiggly lines are just different scenarios. So the blue line is again my control, and then the black line is the results that I observed right underneath the source of ultrasonic waves. So essentially, it's just what would happen below the buoy that they are pretending to set itself in the lake, while the red line are the values that I would obtain if I'm doing the average across the whole treated area. So essentially, the conclusion that I get from this technology is that when I'm looking right underneath the source of the ultrasonic waves, I see some improvement on the algae growth. So essentially, they can prevent something right underneath the source of the waves. But as you start averaging across the treated area, you really don't see that much change because essentially you have a lot of currents moving things around. And even if you are treating algae underneath, there are more algae coming from other parts of the lake. So with that, I would like to come back to the take-home message from this talk, in which essentially I would like to remind you that so far we've been able to develop an in-lake model for Clear Lake, which is capable of doing essentially two main things, which is reproducing how the water moves. So that's our hydrodynamic model. And also reproduce, and also reproduce how the nutrients and the dissolved oxygen and algae is changing. So that's our water quality model. We have used those models already to obtain some preliminary results and evaluate restoration strategy projects that have been recommended to the BRC to mitigate costs. And those technologies for this presentation have been sediment capping, algae and nutrient harvesting, and ultrasonic algae control. And ultimately, what this presentation has shown is that each technology has different capabilities, and there's different aspects that should be explored by the proposal proponents in order just to achieve a successful restoration project. And with that, I would like to again thank you all the team who has been helping me during all these years. It's been already 5 years in the basin. And there is a lot of people behind all this work. So thank you to all of them. But thank you all of you for all your support. Thank you for letting us do this work in your land, of course. And yeah, if you have any questions, please let me know. Thank you.
We have any quick questions for Alicia? Okay.
My question is, are there other algae nutrient harvesting projects around California or around the world that have been successful, and what does a harvester look like? I think that probably there's going to be a talk today. So I guess that I don't have that full information. So I've been more focused on other technology that I will talk in the afternoon. So I would appreciate if you stick around for that presentation.
Just stay here.
Yeah.
Any other questions? Another hand.
Total disclaimer, not scientist here, but I'm always curious with those harvesters, what kind of mitigation is done to protect anything that might come up with the harvester, small fish and that kind of thing.
You mean like preventing?
Yes.
Again, I think that I'm going to refer to the next talk. I'm so sorry. I'm probably modelers here. I can tell everything that you want about oxygenation, but not about harvesters. I'm sorry.
Any other questions?
Related with modeling, maybe?
It's more a comment than a question.
Yes.
I've been approached by so many of these technologies discuss, every single one of them says it will work, right? But the lake is, for my lack of knowing, very unique in the sense that it's ancient, it's surrounded by volcanic soils, and it has a very depleted system that would protect it from the kind of things that are happening today. And so I don't know of one specific technology that would work. There's no silver bullet that I've ever seen. But we have to try something, and maybe it's a combination, like a nice little elixir of things that would eventually get to a better result. But I don't know that this lake will ever see a lack of algae. It's a matter of making it better and more conducive, better outcomes. But I think people are looking at these technologies as if they will change a lake like other lakes. Other ones that I've seen these technologies work on are 10-acre ponds, 50-acre ponds, but not a ancient, massive natural body of water such as this. And so it's interesting. I want to try some of these things, but we really have to go with a grain of salt, and it's going to do exactly what they tell us to do.
And I think that you touched on like many important points. So first of all, we don't want to remove all the algae because Clear Lake is a trophic lake and we want it to be, because all that algae is probably the food web, the base of the food web for our fish. So if we remove it, we kill our system and it's not unique anymore. So first of all, we don't want to do that, but we want to try the issues which are evolving in the years, right? So us, our problem, as you said, it's killing the society and the economic flash of money that you should receive. But essentially what I'm saying is that there are target areas that are suffering, and as you described, accommodation may be the way to go. We need to identify hotspots and see how things can be treated. But at the same time, we need to be strategic and think about the lake as a whole. So in that sense, I would like to just quickly say that I totally agree with what you mentioned before with treating the watershed at the same time as the lake. So the watershed is a source, but the lake is suffering seasonally. So we need to essentially be creative and strategic and have a little both. So yeah, that's my comment back.
Quick question from Charlie, I'm going to switch it over.
Great talk, Alicia. Wonderful use of the model. And I wondered, since you made assumptions about treating a small area, which is feasible for a pilot project, could you use the model to calculate how many of these would you need to get the desired impact? As you say, well, you treat the small area, but the current stripping is well, but what if we put, 100 of these out there? Would it do the desired effect? Would the cost be very large, but maybe you can calculate what that cost would be, and how many of them would be needed to get the desired result.
I already did that scale chart. We did that scale and the numbers are high, right? So I think that essentially, I would like to define how the technologies are actually working with the input from the people who have developed the proposal before actually doing like a real scaling. I tried a decent number of stations, but sometimes the number of stations are too large and probably like not really visible. So I think that, again, coming back to the other question, we should be strategic. So maybe we treat specific areas with things that are more expensive because essentially they need the help more urgently. But if we want to treat the lake as a whole, we probably need to think about dollars, right? And how much is costing. So I think that it's an economical exercise at the same time as a technological challenge. And I think that these kind of tools are helping to try to get at easier. But we really need to try something as soon as possible. Thank you for the question.
Thank you, Alicia. Great presentation.